Good morning, everyone. Myself, Priyadharsini, working as assistant professor in the Triple Department of RMD Engineering College. Today, I'm going to explain a topic from the subject digital signal processing. The topic is about fast Fourier transform. So, what is fast Fourier transform? So, simply we can say it as FFT. It is a method of algorithm. So for computing DFT, we are reducing the number of calculations. So in DFT, we know so the calculations are very high. So and moreover, it will take time to complete that problem. So only we are moving to FFT. So it will reduce the number of calculations. And endpoint DFT is successfully divided into a smaller number of DFT. Next. Radix 2 FFT. Why it is called as a Radix 2 method? So endpoint DFT is converted in the base of 2. So FFT is just we are converting in the base of 2. So only it is called as a Radix method. That is radix is nothing but the base. And n is equal to r power m. R is a radix and m the stage of computation. So how many computations we are going to take? Example, for an example, if I am going to do 8-point DFT, it is 2 power 3. So how many stages of computations I am going to have is 3 stages of computations. So DFT calculation. So first we will go through the DFT calculation and then how it has been transferred in FFT USC. So the number of calculations in endpoint DFT. For example, we know the formula that expression for the DFT that x of k is the summation n tends to 0 to n minus 1 x of m e power minus j 2 pi k n by n. So for k, it is the values are moving from 0 to n minus 1. So if I am substituting the value from 0 to n minus 1, it will be keep on moving. So how many multiplication, that is complex multiplications we are having at the same time complex additions. So we are having n minus 1 complex additions and multiplications and this much complex multiplications we are doing. So from the above equation we can say the number of calculations to calculate x of k for one value of k are n number of complex multiplications and n minus 1 complex additions we are doing. So what is happening in the FFT calculation? So the number of calculations in the radix 2 method. In radix 2 method, m is equal to 2 power m, and so there we will be having m stages of computations where m is equal to log 2 n, in which each stage is having n by 2 butterflies. The butterflies are nothing but the methods. It's a simplified method which we are using in FFT calculation. The number of calculations in one butterfly are one number of complex multiplication, that is one complex multiplication and two number of complex additions we will be using. There are n by 2 butterflies in each stage. So therefore, the number of calculations in one stage are n by 2 into 1 is n by 2 complex multiplications and n complex additions we are using. Calculations of FFT. So m. So m into n by 2 is equal to log to n into n by 2. So n by 2 log to n number of complex multiplications and n log to n complex additions we are doing. So let us see a tabulation comparing DFT and FFT calculations. For example, if 4 is the number of points is 4 point DFT. So complex additions in direct computation method n into n minus 1, so 12, and complex multiplications we are doing 16. So but here by using radix 2 method, the complex additions are only log 2 to the power of 2 square that is 4 is 8, and complex multiplications is n by 2 log 2 n, so 4 by 2 into log 2 to the square, 2 square is 4, so the number of complex multiplications are only 4. So similarly, we can do it for 8-point EFT and 16. So just to see that complex additions in 4-point is 12 and 6 complex multiplication is 16. But here the complex additions for FFT is 8 and complex multiplication is only 4. So this much number of times we are reducing the additions and multiplication. So next we are moving to the twiddle factor. So what is a twiddle factor which we are going to use that in the FFT. So twiddle factor is also called as a phase. Okay. So by the definition of the DFT, endpoint DFT is given by x of k is summation n tends to 0 to n minus 1. X of n e power minus j 2 pi k by n. So we already know this. But here we are taking w base and this is considered to be a twiddle factor e power minus j 2 pi by n where this w represents a complex number. Okay. Hence the phase or arguments is w is minus of 2p. Therefore, when a number is multiplied by this twiddle factor, okay, only its phase changes, but magnitude remains the same. Okay. So w power k is e power minus j 2 pi into k. Example which is showing the difference between the DFT and FFT. In DFT, for example, if I want to add the numbers between 1 to 5, so how you will add 1 plus 2 plus 3 plus 4 plus 5. But here, if I am going to do FFT, DIT method, n into n plus 1 by 2. So this is a short form I am using and my answer is 50. The same thing I can do with the DIF also. So DIF is one more method of in the DIF of t. So 2 by that is inverse. So 2 by 30 and 1 by 15 again I have to take the inverse. So this much number of additions I am doing in DFT, but the same answer I am getting with the simplified one. So this is an example explaining between DFT and FFT. Types of FFT. So in the fast Fourier transform, there are two types. One is DIT, another one is DIF. DIT, DIT is nothing but decimation in time and decimation in frequency. What is DIT? A large signal is decimated into small signal by using the time period. And what is DIF? A large signal is decimated into the small signal by using frequency. Okay, so one example we will see with the DFT and again you will know with the FFT. Okay, so here they are saying compute the DFT of the sequence. So they are given x of n as 0, 1, 2, 1. Sketch the magnitude and phase spectrum. Okay, so they are asking us to draw the magnitude as well as the phase. So solution we are going to start and we know the formula. So the definition of the DFT, discrete Fourier transform is x of k summation n tends to 0 to n minus 1. X of n e power minus j2 pi k n by n. So n minus 1 is nothing but 4 minus 1, 3. So e bar minus j2 by k n by n. Okay. So you substitute the value. So x of 0 e to the power of 0 plus x of 1 e power minus j2 that is pi k by 2 and similarly x of 3. So like this if it is going and the final answer after substituting the final answer is going to be for when k is equal to 0. Okay. So the final answer is 1 plus 2 plus 1 plus 1. So answer is going to be what? 0. Okay. And similarly, when k is equal to 1, so k is equal to 1, the same thing, the k value will be 1 and the n value will be moving from 0, 1, 2, 3. And if I am substituting all the values, the final answer is 2 angle 180 or 2 power pi. So like this, I can be able to find out between 0 to 3 and after that I am framing the magnitude and phase spectrum. So this is a generally how we will be doing by using the DFT we are seeing. Then the basic butterfly diagram. So now we are moving to the FFT means we should know how the butterfly diagram or the basic diagram has to be drawn. So here, so this is the basic butterfly diagram. So here it's a even component and odd component. Here the twiddle factor will be there. So now you see the even component plus it will be multiplied with the twiddle factor. It will be going to the ladder. So even component plus the twiddle factor into odd component. And here you will be having the negative sign. Even component minus the twiddle factor into the odd component. So here xe of k is nothing but even component. X naught of k is the odd component and wn of k is the twiddle factor. So the stage 1 means that is going to be the 2 point, stage 2 means 4 point, and stage 3 means 8 point. So this is the 4-point butterfly diagram. So this is I've explained by using DIT method, that is decimation and time. So 4-point butterfly diagram, how we are drawing. So first, so this is the 4-point. So 4-point means you'll be having the 4 lines to represent that. And we have to write the input, and after that we will be getting the output. Okay. The input will be in the form of the reversal order. So we have to do the bit reversal and write the inputs. And similarly, in the odd component, you should have the twiddle factor and as well as the negative sign will be coming. And the normal calculation. So x naught plus w2 naught x2. Okay, and here x naught minus will be coming. Same thing, minus w2 naught into x2. Whatever may be the naught value, it is representing only one. Okay, and x1, and the same thing will be coming here. So for x1 and x2. And this is entering to the 4-point. So if this is entering to the 4-point means 4-point twiddle factor has to be used. So the twiddle factor for the 4-point stage is 1, and as well as if I am substituting w4 1, that is e power minus j 2 pi k by n. Okay. So if I am substituting the value of n going to be the 4, and my answer is minus j. So here the first even component will be joining with the first odd component, and I will be getting this answer, and similarly the second with the second odd component. And this is from the top towards the bottom, and similarly bottom towards the top. Only the sign alone will be changing. So like this we have to do the 4-point DFT. So especially in the DIT, whenever I am using DIT, that is decimation in time, the input has to be bit reversal and output should be in the normal order. So first example we are going to see is, that is a 4-point DFT, how to solve. Okay, so now we are going to see how to do the bit reversal and as well as to write the sequence everything. Okay, so 4-point DFT is, for example, x of n is x of 0, 1, 2, 3. Step 1, separate the odd and even components. We can separate it, and for that we have to do the bit reversal. Bit reversal means you write the values in the binary value 0, 0, 0, 1, 1, 0, 1, 1, and then you reverse the numbers and you will be getting the even pair and odd pair. And then calculate the twiddle factor, W and K. K value is between 0 to n by 2 minus 1. Since it is going to be the 4-point, 4 by 2. So 2 by 2 minus 1 is 1. So 0 to 1. So two twiddle factors will be coming. One value taking 0 and another value is taking to be 1. If I am substituting 0, the answer is 1. If I am substituting 1, e power minus j 2 pi, k value is 1 and n value is 4. If I am substituting like that, my answer is minus j. So like that, I am getting the twiddle factor 0 and 1. And output sequences as it is. So whatever we are getting, the same in order we can get the output. So no need of the bit reversal in the output. Only in the input side we have to do the bit reversal. So one example we are going to see, compute the 4-point DFT of the sequence x of n is 0, 1, 2, 3 by using what method? DIT method they have said. So in DIT method, what is the step 1? We have to do the bit reversal. Step 2, get the twiddle factor, and step 3, output will be in the same sequence. So if I am doing the bit reversal, uh, the first, accordingly, you will be doing the pass, getting the pass. First is x of 0 and x of 2, and next is x of 1 and x of 3. And similarly, calculate the twiddle factor. The two twiddle factors are 1 and minus j. Okay. So we will start the problem now. So since it is a 4-point, so how many stages will be coming? 2 stages. First is the 2-point, second is the 4-point, and you draw the lines in the same order, that is x of 0, x of 2, x of 1, and x of 3. Since the first stage is the 2-point 2-point stage, the twiddle factor is 1. So this is even component plus the odd component. So 0 plus 2, it will come as it is. And here 0 minus 2. And here 1 plus 3, and here it is 1 minus 3. So these are my answers I am getting. Okay. And the next is, it is entering into the 4-point. So here the 2 will be coming as it is. The next odd component is 4. It will be multiplied with the twiddle factor. This value is 1 only. So 4 into 1, 1. So it will be moving to this ladder. So 2 plus 4, 6. Okay. And here it is minus 2. And this component will be coming here. So minus 2 into minus j. So that is going to be plus 2j. It will be the ladder. Similarly, the other two components will be there. So these are my answer. Answers are 6 comma minus 2 plus 2j, minus 2 and minus 2j. So like this we can able to obtain the answer for the 4 point earlier. Thank you.